Hey everybody, welcome to AP Chem Unit 2. In this unit, we're going to mostly be talking about the different types of bonds and the different types of compounds, what their properties are, depending on the type of bond that they have, and how we can kind of distinguish between the different bonding types. So all types of chemical bonds relate back to the octet rule. So hopefully you remember this octet rule from baby chem, but elements tend to gain, lose, or share electrons to acquire a full octet. A full octet is 8 valence electrons, and valence electrons, if you recall, are the furthest electrons from the nucleus. So there are some exceptions to this. In the first energy level, n equals 1, a full octet would only mean 2 valence electrons. That's just for hydrogen and helium. There's only one s orbital in the first energy level, and so there's no way to fit 8 valence electrons. And there's also no way that the 1 or 2 protons in the nucleus could hold on to that many valence electrons, eight full valence electrons. From energy level 2 through 7, a full octet would mean 8 valence electrons, so that would be a full s orbital and a full p orbital. Remember, there can be 2 electrons in an s orbital and 6 in a p orbital, so 2 plus 6 gives us 8. However, within that range of energy levels, some of the elements can get more or less than 8 valence electrons, and we'll talk about these exceptions later, but there's a few reasons why they can do that. And like I said, we'll get into that more in later lessons during this unit. But what you need to know right now is that these elements are trying to gain, lose, or share electrons to get that full octet. And the most common way for them to do this is to form bonds. So a chemical bond is just a force that holds groups of atoms together. And once they are connected together, they function differently. They have new properties, chemical and physical properties that are unique to that combination of elements. So the different properties of whatever material we're looking at can help us to determine the bond type. So some of the properties that we'll be looking at are melting point or freezing point, and then also boiling point and condensation point, I guess, as well. The hardness, the electrical and thermal conductivity, solubility, how they form a solution with water or other solvents, the energy of the bonds, things like that. All of those properties that we can measure can tell us what type of bond there is, how strong that bond is, things like that. There's 3 types of chemical bonds that we'll be looking at. There's ionic, covalent, and metallic. Covalent can be divided into polar and nonpolar, so we'll discuss that as well. Ionic bonds are the attraction between oppositely charged ions. So in an ionic bond, the atoms become charged in order to fulfill the octet rule. So this is where they lose or gain electrons. Losing electrons gives them a positive charge because electrons are negative, while gaining electrons would give them a negative charge. So typically, the ionic bond forms when you have one atom that loses electrons easily. It has a low ionization energy. And that element would react with an atom that has a high electron affinity. It really wants to gain electrons. So you wind up with one that becomes positively charged and one that becomes negatively charged. So these elements will lose or gain electrons to get that full octet, or we can also say that they do this to get the electron configuration of a noble gas. That's kind of the goal. Noble gases are the most stable. Typically in an ionic bond, we're dealing with one metal and one nonmetal. In covalent bonds, the atoms will share electrons in order to get that full octet or to have the noble gas electron configurations. So as we said before, for the octet rule, they can lose, gain, or share. Losing and gaining is associated with ionic bonding. Sharing is associated with covalent bonding. Covalent bonds only occur between nonmetals. So if you see a metal in the formula, it's not going to be a covalent bond. So the electrons that are shared wind up spending most of their time between the two nuclei of the atoms that are involved in the bond. So the nuclei are positively charged, and they're going to be attracted to that negative charge of those shared electrons. And that's what holds this bond together. What hold these atoms together in this bond is the fact that both of those nuclei of the atoms are attracted to the electrons that are spending time between them. And those electrons are attracted to both of those nuclei. So while we do distinguish between ionic and covalent, there is some ionic character in covalent bonds as well. Ionic character is just kind of a measure of how much the difference or the size of the difference in electronegativity between the two atoms. So there's no such thing as 100% ionic character, but if you have greater than 50% ionic character, then we classify that as an ionic bond, and less than 50% is going to be covalent. So the higher up you go on that ionic character scale within the covalent bonds, the more polar the bond will be, because those partial charges of the atoms is going to be greater. That gives us a polar bond. The smaller the ionic character, the more nonpolar that covalent bond will be. So polar covalent bonds are caused when the electrons are not shared equally between the two atoms. And this is due to the fact that those atoms have a difference in electronegativities. So one atom is going to be more attracted to the electrons in the bond than the other atom. So those electrons are going to spend more time around the more electronegative atom, giving it a slightly negative charge, and less time around the less electronegative atom, which gives it a slightly positive charge. But these are not like ionic charges where it's totally taking the electrons. It's just, we call it a partial charge. It's just kind of charged because those electrons are still shared between them. So you can see in this picture, this is the Greek letter delta, lowercase delta. So you have the delta plus, delta minus. That shows us the partial positive and partial negative charges on this molecule. One thing that's interesting about polar molecules is that if you place them in an electric field, they will align according to their charges. So you can see here they're just scattered, but when we put them in an electric field, the positive charges line up towards the negative side of the electric field, and the negative charges line up towards the positive side of the electric field. So just to kind of review, electronegativity is how strongly the atom will attract electrons within a bond. So it must be a bonded atom for us to look at electronegativity. We do have electronegativity values, and there's a chart in your book that gives you the electronegativity values for the elements on the periodic table. A guy named Linus Pauling created the method for figuring that out, figuring out what the electronegativity values are. But typically, if we look at our periodic trends, the electronegativity will increase from left to right, going across a period, and it'll decrease going from top to bottom down a group. So what that means is fluorine is the most electronegative element. Its electronegativity value is about 4.0. And cesium and francium on the opposite side of the periodic table are the least electronegative with a value of about 0.7. So like we said, the atom with the greater electronegativity value will get a slightly negative charge. We call it a partial charge because those valence electrons that are being shared are going to spend more time around that atom. They're going to be closer to that atom. The atom with the lower electronegativity will get a partial positive charge for the opposite reason. Those shared electrons are going to spend less time around it. The greater the difference in electronegativity, the greater those partial charges will be. So if you have, fluorine and hydrogen, that's going to be a much bigger difference than fluorine and oxygen, just based on how far apart they are on the periodic table. If we add up the partial charges in any molecule, it's always got to equal the overall charge on the total compound. And in general, for polar molecules, that total charge is going to be 0. So those partial charges basically wind up canceling out to form an overall charge of 0. So to figure out the type of bond between ionic, polar covalent, or nonpolar covalent, we need to look at the difference in electronegativity. So if we have two atoms that are exactly the same, like let's say we're looking at a bond between oxygen and oxygen, right? O2. That is going to be a nonpolar bond because the difference in electronegativity will be 0 since they both have the same electronegativity value. Anything from 0 to 0.4 is going to be a nonpolar bond. That difference in electronegativity from 0 to 0.4 is not strong enough to create partial charges. If we have a difference between 0.5 and 1.9, that is considered a polar covalent bond. And then anything greater than that, 2 on up, is going to be an ionic bond. So we can determine which type of bond we're looking at by comparing those electronegativity values. So to order the bonds in order of increasing polarity, we need to look at their differences in electronegativity. So first of all, just looking at this list, we can see that we have one bond that has identical atoms, which means that the difference in electronegativity is going to be 0. So that's going to be the least polar out of all of these. So we can start by writing HH as our least polar. We also can see that FH here, we know fluorine has the highest electronegativity on the periodic table. And we're comparing all of these elements to hydrogen, so we can say with certainty that this is going to be the greatest polarity. So we can put that at the opposite end. Now, to be certain with the others, we should check their electronegativities before filling them in. So we look at our periodic table in the book. This is on page 357, and we can find the elements that we're dealing with. So we look up each element and then we'll subtract their electronegativities to find the difference. So oxygen has an electronegativity of 3.5 and hydrogen is 2.1. Chlorine is 3.0 and sulfur is 2.5. So just by looking at these, we can see that the next smallest difference is going to be between 2.5 and 2.1, because that will only give us a difference of 2.4. And then we can see that the difference between 3.0 and 2.1 is going to be less than 3.5 and 2.1. So our chlorine bond will be next, and then we can fill in this one. The last type of bond is metallic. A metallic bond is a bond between two metals, obviously based on the name. But the way that these bonds work is kind of weird. So normally we're used to electrons being gained, lost, or shared between these electrons, or between these atoms, sorry. But in the metallic bond, basically you have all of these metal atoms that are identical, but they will essentially lose those electrons and kind of share them all between the different metal atoms. So we say that those valence electrons from the metal atoms are delocalized, which means that they are not tied down to any one individual atom. They can kind of spread out between this network of positive metal ions and just kind of flow between them. So this gives metals some unique properties because those electrons are allowed to move, which is not the case in most other types of compounds. So because those electrons are allowed to move, metals can do things like conduct electricity because electricity is just electrons. And so it can push these electrons through the metal because they're allowed to migrate from one side to the other. In this example, we're asked to figure out the bond type for each pair of atoms. So the first thing we can do is look for ionic bonds because we know that that will contain a metal as well as a nonmetal. So we see in this first one, we have lithium, which is an alkali metal, and nitrogen, which is a nonmetal. Metal plus nonmetal means it'll be ionic. The only other one that has a metal and a nonmetal is here, aluminum and bromine. So again, we have a metal and a nonmetal, so we're going to have an ionic bond. Next, we can look for metallic bonds. Metallic bonds would be between two metals. So we see copper and copper here, two metals, right? So that would be metallic. And then lastly, we can look for our covalent compounds, which these are all nonmetals with nonmetals. But once we figure out that they're covalent, we need to figure out whether they're polar or nonpolar. So again, that takes us back to looking at the electronegativity values. So for oxygen, we have a value of 3.5 and carbon is 2.5. That's a difference of 1. And anything greater than 0.4 is polar. So this is going to be polar covalent. For this one, carbon and hydrogen, again, we have two nonmetals. Carbon was 2.5, hydrogen is 2.1. So that's a difference of 0.4. So that is nonpolar. Lastly, we have sulfur and sulfur. We don't even need to look up their electronegativities because if you remember, if you have the same two atoms, that difference will always be 0, which means it must be nonpolar.